Okay, so this is a set of notes on what we're going to call improper integrals. Let's take a look at an example of something that would be improper. Okay, so this is an integral from 0 to infinity of dx over 1 plus x squared. Now, if you were to graph this, you're going to get a curve that looks something like that. And this is the area under the curve going this way. And the question that we're asking here is this finite, the area, even though we're going from 0 all the way out to positive infinity? And we're assuming that this thing is like asymptotic. So the way that we handle this is that we actually get rid of that infinity up there by making this the limit as a approaches infinity of the integral from 0 to a of dx over 1 plus x squared. This is going to be the limit as a approaches infinity of, well, that's the inverse tangent of x from 0 to a, which means that I now have the limit as a approaches infinity of the inverse tangent of a minus the inverse tangent of 0. Well, if we follow this, this is going to go to 0, right? So this is just the limit as a approaches infinity of the inverse tangent of a, which we know goes off to pi over 2. So believe it or not, the area under that curve from 0 out to infinity is going to simply be pi over 2. Now, we don't always have to have bounds going to infinity to see something like this happen, so we'll work a second example, and one that has a vertical asymptote instead of a horizontal asymptote, and see if we can make this work. Okay, so we have the integral from 0 to 2 of dx over the cube root of x minus 1. So if we did a sketch of this, we would get a vertical asymptote at 1 and a curve that basically looks like this. Okay, so we're going to ask if I go from 0, so that's this section, to 2, that's this section, and I add those, do I get something that is finite? Okay, so literally here I have to break this into two limits. I need the limit as a approaches 1 for the negative side. Sorry, it's going to be a approaches, 1, because that's where the asymptote is, from the negative side of 0 to a of, let's just make this what we will work with in the problem, x minus 1 to the negative 1/3 dx plus the limit as b approaches 1 from the positive side, right, of b to 2 of x minus 1 to the negative 1/3 dx. Alright, so we can do a little bit of work here. We can probably work them both at the same time because the antiderivatives are the same. So we could take the limit as a approaches 1 for the negative side, and this is going to give me, let's see, I'm going to get x minus 1, right, to the negative 1/3. So I'm going to end up with a 2/3 power here, right? So this is going to be 3/2 in front of that, right? From 0 to a. And the same thing here is limit as b approaches 1 from the positive side, right? And this is also going to be 3/2 x minus 1 to the 2/3, now from b to 2. Okay, so this is the limit as a approaches 1 from the negative side of 3/2, right? And let's see. I'm going to get a minus 1 to the 2/3 here. And that's going to be minus -1 to the 2/3, right? Because 0 minus 1 is -1. Okay. And then we're going to take the limit as b approaches 1 from the positive side. And let's see what happens here. If I put 2 in there, right, so we're going to go to 3/2, right? Put 2 in there, 2 minus 1 is 1 to the 2/3. And then this is going to be minus b minus 1 to the 2/3 end bracket. And I think I've got that. It's just 1. Okay, so let's see what happens. We go limiting here, right? As I'm approaching 1 from the negative side, this is going to go to 0, right? So this is going to 0. Negative and a negative, so -1 to the 2/3 is, let's see, -1 to, so that's going to be +1, right? So this is -1, so this is going to be -3/2, right? Because this is +1, negative. So this is 3/2 times -1 is -3/2. We take the b to the first here. That's going to give me 1. Oh, sorry, that's a 1 there, right? So 1 minus, let's see, 1 minus 1 is 0. So this is just going to be 3/2. Okay, slow down and work that out by putting the 1 in here, putting the 1 in there, and you'll get -3/2 plus 3/2, which works out to 0. And that kind of lines up with my drawing, that the area under the curve and the area over the curve are symmetric. So yes, this integral works out to have an area of 0. Huzzah. So it is possible, given a infinite value in the game here, where I either have a horizontal or a vertical asymptote, to end up with a finite area under a curve bounded by that.